Okay, so in this first example, water is flowing out of a reservoir such that the depth of the water is a decreasing function of the number of hours since water was released. So the number of hours is going up, and the depth is a decreasing function. Engineers measure the depth of the water, and their results are shown in the table. Find an exponential equation. So this is just a regression problem, so we're going to enter our data. So we hit Stat, Edit, in list 1 of 2, 4, 8, 14, and 20, and 44.7, 36.8, entering all this stuff, and 15.1. Okay, so now when it comes time to run a regression, remember your points you put in list 1 and list 2. So when I do my scatter plot, second y equals, I'm going to turn it on. I want to make sure I'm using my x coordinate as list 1 and my y coordinate as list 2. Yours should all already be that way. I was just doing some other things on here earlier, so those changed. When I go to create my scatter plot, my window needs to reflect my numbers. So my x's are from 0 to 20, so I'll get 0 to 20, and my y's are as high as 44.7, as low as 15, so I'll go from 0 to 50, and that should cover everything. So when I look at my scatter plot, I get that. I also got this line here. Remember, that's because I probably have some line or some curve in the y equals, and sure enough, I do have 2 there. So there's just my scatter plot. So you can see the exponential pattern. And to run our regression, Stat, Calc, and run your exponential regression. Again, my x list should be L1 and y list should be L2. Yours are probably already that way. And then calculate. So my A is 47 point along decimal. They say the nearest hundredth. So y equals, my A is 47.97 would be my nearest 100th. Times my B value is 0.94. Might want to put that in parentheses just so you can see it better, to the x power. And I'm going to use my equation to predict the depth of the water after 2 days. 2 days would be how many hours? Okay, 2 days is 24 hours. So I'm going to plug in an x of 24 right here. So 47.97 times 0.94 to the 2 days, I'm sorry, 2 days is 48 hours. Back that up. To the 48th power. And I'm going to get 47.97 times 0.94 to the 48th power. And my depth is only 2 point, and it says round your depth to the nearest tenth. So 2.5 feet. Okay, a couple other things to just make note of, just as a review. If that's the base, then at what rate am I losing water? What percentage am I losing every hour? Okay, if my base is 0.94, that must have been 1 minus 0.06. So I'm losing 6% every hour. I'm retaining 94%, and that's what that base number tells me. But 1 minus 0.06 tells me that I'm losing 6%. How would you characterize the strength of the correlation? That's actually something we haven't done yet, so we're going to omit that one. Okay. I will, however, quickly graph this. 47.97 times 0.94 to the x power, and we'll see how close it is to all of our points, and that's pretty good. With the exception of this point here, that's a pretty good best fit line. Best fit curve, I should say. It's not a line. Alright, we get into the good stuff with stat, simulation type stuff. So a survey of 40 high school students was done to determine how many of them liked fresh fruit. The school will offer a fresh fruit option if more than 30% of students like the fruit. So they surveyed 40 people, and 9 of them stated that they liked fruit with lunch, so 9 out of 40. Okay? 9 out of 40 on your calculator is only 22.225, or in other words, 22.5%. So obviously that one sample alone is not enough to encourage the cafeteria staff to put fruit on the menu. But simulations were done with a population proportion of 0.3 and a sample size of 40 to see how likely a sample of 40 would be to only have 9 who liked fruit. Okay, the results of the simulations are below. So we got 0.225. So this is 0.2, 20, 22, 24, 26. Yes, this is probably 0.22, 0.24, 0.26, 0.28. So 0.225 would be right here and below. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 out of the 100. The observed sample proportion we saw was 0.225. Round to the nearest hundredth is 0.23. If the true population proportion is 0.3, like our simulation suggested, then how likely is it, based on the simulation, that a sample of size 40 would have 9 or fewer students say they like fruit for lunch? And that was what I just counted, and I forgot 6, 10, 12, 14 out of 100, so 14%. So there's a 14% chance that we really could have a population of the 30%. That could really be the favorability of the whole population. So should the school conclude that they should not serve fruit for lunch, explain your reasoning. This could go either way in Part C. Again, it's how you sell it. So you could say, and actually, unless this is, less than 5%, I would say, carry on with the study. So I would say, should the school conclude that they should not? I would say no. They should continue to survey more people, or simply serve the fruit, because there's a 14% chance the result of their sample was so low due to really the coincidence of who they surveyed, which would be called sampling variability. Okay? If you wanted to phrase it the other way, you would say there's an 86% chance that this does not come from a population of 30%. And 86 is kind of high, so that's arguably, if you want to phrase it that way, I think the 86% chance that this population is actually not 30% favorable is kind of would be the vantage point I would argue the yes from. But I would say no. Really, unless that's below 10%, but definitely below 5%, would be the cutoff in my eyes. But again, it's all how you sell it. If we look to the back, number 17, a population that is normally distributed has a mean of 164 and standard deviation. I see normal distribution. They give you the mean and the standard deviation. I'm immediately sketching my normal curve. I don't even read the question. Just sketch it. And we'll hang on to the standard deviation until later. If a sample of size 50 was taken, what is the probability its mean would be greater than 168? So what are the chances it would be greater than 168? So this is kind of the area of the shaded region. This is your norm CDF kind of question. So we want the area under the curve starting at 168 up until 999 with a mean of 164 and a standard deviation of 18.65. And then just type that into your calculator. So on your calculator, in the event that you forgot, it's second and then this VAERS number, so second VAERS norm CDF. My lower bound is 168, my upper is 999. If you want to do a bunch more 9s just to be safe, you can. My population average was 164, and my population standard deviation is 18.65. Paste that in, and you're going to get your percentage chance. It's 0.415, which would be 41.5%. That's the nearest tenth of a percent. So norm CDF, pretty straightforward. I'd be pretty confident you're going to see something like that on your regions. 18. A recent experimental study. 40 participants broken into two groups of 20 and 20, I assume. Group 1 maintained a regular exercise routine. Group 2 maintained the same exercise regime, but also drank a cup of green tea each day. At the end of a month, the weight loss of each of the 40 subjects was recorded, and means for each group were produced as follows. So I'm already guessing that they're trying to figure out, by keeping as much the same as possible and only changing the fact that one group drank green tea and the other one did not, they're wondering if green tea has something to do with weight loss. So group 1, which is the no tea group, and group 2, which is the tea group. What was the value, what was the difference in their averages? So group 2 minus group 1 is 8.6 minus 5.3. So the observed difference that we actually saw happen was 3.3 pounds. So we saw that group 2 actually did lose 3.3 pounds more, which at first glance makes us think, okay, maybe the tea does make you lose weight. Okay? Explaining the meaning in terms of the experimental study, the group that drank tea lost 3.3 pounds more on average. Now we're going to do a simulation. Weight losses from the 40 participants were randomly shuffled into two treatment groups, 100 simulations. The distribution of the differences in sample means is shown. So our 3.3, here's 3, here's 3.5. So our 3.3 is here. So by coincidence, when these were all shuffled randomly, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 out of 100 times we got something this high or higher by coincidence, meaning based on the way that these people were randomly grouped. So based on this distribution, how significant is the induced treatment variability to the weight loss of the participants compared to natural variability? Explain your thinking. I would say there is only a 9% chance that the weight loss difference was due to coincidence. Oops. Because there's 9 out of 100 simulations were by coincidence, which means there is a 91% chance that the green tea actually had some part in the weight loss. Okay. And the last one. In a survey of 500 people, 45% of them reported that they were going to vote for candidate A. The margin of error was 2%. Explain what this means in terms of the actual support for candidate A. So 45% is what they found in their sample, but the margin of error is plus or minus 2%. So what this means is that we could have as high as 47% favorability for candidate A or as low as 43%. Okay, so we are 95% confident that the favorability for candidate A falls between those two numbers. We are 95% confident that the favorability for candidate A will be between 43 and 47%. And that's that. Obviously, you have the rest of the packet to use as a study guide, but those, I took one kind of each of the main types that we might have to look at. So hopefully that was helpful, and good luck on your test.